let's spend a little time talking about work. Um, so, when we've done this before, we've been talking about it in terms of energy. You guys are used to the idea that if there's a pie full of energy, half of it's E kinetic, half of it's E gravity, that we can move energy from one piece of the pie to the other, and that the pie doesn't get any bigger. But if we want the pie to get bigger, we have to find some way to put energy into it. And we talked about processes of doing this. One of them was doing work or working. Now, some physics teachers are going to go nuts and tell you that work is not energy, that working is a process. But most traditional physics books just say work and energy are the same thing. So I'm just going to go with that for now. Okay? And there's a formula for figuring this out. When you do something like a ball rolling down a hill, we're just saying that the energy is going from E gravity to E kinetic. Or, by the same token, if there was a ball rolling quickly, and sorry, that's supposed to be hill, not an arrow there. If there was a ball rolling quickly after someone had given it, let's say it was going, I don't know, 30 meters per second, that ball would roll up the hill, and all of its E kinetic would get converted to E gravity. But let's just say that we've got a ball sitting at the bottom of the hill and we want to get it to the top. You're going to have to do something to get it there. You're going to have to apply a force to the ball over a distance to get it to the top of the hill, which brings us to this idea of work, right? Let's just get the formula part out of this right of the way. Work is equal to force times distance. And since working adds energy to a system, then we're going to use the same units of energy for work and energy. So that's joules. And the unit of force is a Newton, and the unit of distance is the meter. So a joule is a Newton meter. All right, so your abbreviation, of course, is just going to be work equals force times distance. Again, force is in newtons, distance is in meters, so a joule is a Newton meter. Okay? So let's talk through some things that can be pretty simple with this, and then things that can be a little confusing. So one example would be, let's say that you've got a box, all right? And you're going to have a person pushing that box along, all right? So let's say that this box has a mass of, 100 kilograms, okay? If we have to apply force to it, we don't really care about the weight of the box. Now, when we do free body diagrams later, we'll talk about how friction works into this. But if I apply a force on this box of 70 newtons, and I do that for a distance of 3 meters, work equals force times distance, 70 newtons times 3 meters would be 210 newton meters, or 210 joules. The weight of the box is irrelevant. It's just the amount of force that I applied to overcome friction and to get the box moving to get it there. Okay? Other examples. Let's say maybe I've got some sort of a pulley system here. I got a rope over a box, and I've pulled a bunch of rope through the pulley, and I've raised this box 1 meter, and I applied a force of 20 newtons to it. All right, 20 newtons for a distance of 1, and this pulley just redirects it. It doesn't give me any mechanical advantage. 20 newtons times 1 meter would be 20 newton meters, or 20 joules of energy. All right, another situation. Let's say that I've got, well, we sort of covered it already. If I had a ball at the bottom of a hill and I wanted to get it to the top, I would apply a force to get it up the hill. Now here's the trick. There's two situations that can be pretty confusing. if you have a person who is carrying a big box and walking, the force they're applying right now is really just to lift the box. Now, it does take them some energy to work, but if we're talking about work done on the box, if you carry a box all this distance, technically you didn't really do any work on the box. You were just holding it up. So that can be kind of a confusing thing. Also, let's say that you have a big wall and I have a person pushing really hard on the wall. They're going to start sweating and they're going to start getting tired and their heart rate's maybe going to go up. But in terms of work done on the wall, technically they didn't do any work on the wall. Now you could make the argument that the person's heart is pumping fast, so there's actually a force of the heart pumping blood, and that blood is moving a distance through your veins. So maybe you're doing work on the blood in your system, but you're not doing any work on the wall technically. So you only consider the object and the force on it and the distance that it's gone. So that's pretty much the work, force, and distance video here. You can use this on some of the worksheets that we've been talking about in class.